we'll get started with rudiments of definite integrals today. All right? Now, some very basic stuff with which you've already bred familiarity. One, if integral fx dx is phi x plus c, if integral fx dx is phi x plus c, then integral fx dx a to b actually means phi b minus phi a. The constant of integration gets cancelled. Right? All of us understand this, isn't it? Also, integral fx dx a to b, this x that appears here is only temporary. It will get dissolved the moment you supply the limits. It will get completely dissolved, right? Therefore, integral fx dx a to b is the same as integral ft dt a to b. It does not matter whether you are saying integral sin x dx 0 to pi by 2 or integral sin t dt 0 to pi by 2. This x here that appears has only a temporary existence. It dies the moment you supply the limit. So whether it's x or it's t, you're talking of the same structure over which these limits are applied. Clear? Also, the other thing that is very evident from here is if integral fx dx from a to b is phi b minus phi a, then integral fx dx b to a is going to be phi a minus phi b, which actually is minus integral a to b fx dx. Yes or no? Right? If you swap the limits, then a minus sign automatically will appear. Right? Now, integral fx dx a to b, we'll be able to show, not right now, but we'll be able to show integral fx dx a to b actually represents the area under the graph of y equal to fx from x equal to a to x equal to b. Integral fx dx a to b represents this area, shaded area. Integral fx dx a to b represents the shaded area. Now, very clearly, if fx is positive, then this area is positive. However, if fx is negative from a to b, see, these are all negative fx's for all x's between a and b. If fx is negative, then this area, shaded area, will be deemed negative, right? Part of the graph could be above the x-axis, part could be below the x-axis. Part of it would be positive, part of it would be negative. Which means, suppose I had something like this. Integral fx dx a to b, then what it represents is this area, which is negative, plus this area, which is positive. It will represent the algebraic sum of these two areas, and the net effect could be positive or negative. Does, right? So this will represent the integral fx dx will represent this algebraic area. This positive plus this negative, it could be either positive or it could be negative or it could be 0. Right? Now, so very clearly, if fx is greater than or equal to 0, then integral fx dx a to b will be greater than or equal to 0. If fx is less than or equal to 0, then integral fx dx a to b is going to be less than or equal to 0. Right? And if part in a given interval, part of fx is positive, part is negative, then a to b could either be positive or negative or 0. Now, if in a given interval, say this is the graph of y equal to fx, and this is the graph of, say, y equal to gx. Between x equal to a to x equal to b, in the interval a to b, you realize that fx is greater than gx. Right? That means the area under fx will be greater than the area under gx. So I can say if fx is greater than gx, then we can apply this property. Fx dx from a to b will be greater than gx dx a to b. However, this we couldn't have done in differentiation. If fx greater than gx at a certain point, we couldn't have said f dash x greater than g dash x. But in integration, we can say that over an interval. That's an acceptable thing, right? Now, sometimes there could be a function which is not continuous in an interval. Sometimes there could be a function not continuous in an interval. For example, y equal to fx could be like this. In the interval a to b, say these are the points of discontinuity. C1, C2 are the points of discontinuity. Right? And now, when I say integral fx dx a to b, then what it means is the area from a to c1, and then c1 to c2, and then c2 to b. So I will then have to break this integral into smaller pieces, breaking at c1 and c2. That means this would be like integral fx dx a to c1 is what I'll compute first, right? Which would give me this area, right? And then I'll go with c1 to c2, which would be this area. And then we'll have to go from c2 to b, which would be this area. So for a function that is piecewise continuous, continuous here and then here and then here, so we'll have to break it up into pieces. And c2 to b fx dx. Right? For example, say I talk of integral box x dx, x runs from 0 to 3, say. Box x is discontinuous at 1 and 2, right? In the interval, it's not continuous in the interval 0 to 3. It's discontinuous at points 1 and 2. So what I'll do is, I'll break this interval 0 to 3 as 0 to 1, and then 1 to 2, and then 2 to 3 is what I'm going to do with this, right? So then, this is like integral 0 to 1. Now, when x goes from 0 to 1, box x will be 0, 0. Then I'll go from 1 to 2. In the interval 1 to 2, box x will be 1. So I'll like a 1 dx. And then from 2 to 3, box x will be 2 dx. This is what we do for box x, right? Suppose I have integral box of x squared dx. X goes from, say, 0 to 2. Now, in the interval 0 to 2, this box of x squared would be discontinuous every time x square is an integer. That means, when x square is 1, and so on and so forth, right? Whenever x square is an integer, then it's going to be discontinuous. What I do is, I write this as, when x runs from 0 to 1, x square runs from 0 to 1, and box of x square will be 0. Now, when x runs from root 1 to root 2, when x runs from root 1 to root 2, then x square runs from 1 to 2, box of x square will be 1. Then x goes from, say, root 2 to root 3. Then x square goes from 2 to 3. Then box of x square will be 2. Box of x square will be 2. And then root 3 to root 4. Root 4 is 2, right? So x square, when x goes from root 3 to root 4, x square goes from 3 to 4, box of x square will be 3. Box of x square will be 3. This is all that we need to evaluate then. So sometimes we'll have to break up an interval into its pieces, right? Can I wipe this off? Suppose I have mod of x minus 3 dx. X goes from minus 1 to 5. This one changes behavior at x equal to 3. To the left of x equal to 3, it's 3 minus x. To the right of x equal to 3, it's x minus 3. That means x equal to 3 is the point where we would have to break it up, right? So we'll go from minus 1 to 3, and then we'll go from 3 to 5. So minus 1 to 3 is x less than 3, and it's going to be rendered as 3 minus x dx. And then 3 to 5, when x is greater than 3, mod x minus 3 will be x minus 3. Etc. Yes or no? Simple, na? Now, Now, say there are times when you will have to estimate an integral. There are times when you would have to estimate an integral. You cannot integrate that function, but you will have to estimate that integral. See, for example, if someone said e power x squared dx 0 to 1 and expected you to be able to integrate e power x square, then that would be too much. E power x square is not an integrable function. But the graph of y equal to e power x squared does exist. Right? The graph of y equal to e power x squared is like this. No. From 0 to 1. From 0 to 1, this is the graph of y's e power x squared. Right? Now, the graph of y's e power x, see, in the interval 0 to 1, which is bigger? E power x square is bigger or e power x is bigger? E power x is bigger. Because x square is less than x. In the interval 0 to 1, x square will be less than x. Right? When x lies in the interval 0 to 1, x square will be less than x. So, e power x square will be less than e power x. E power x square will be less than e power x. Right? So, then I can conclude integral e power x squared dx 0 to 1 will be less than e power x dx 0 to 1. Yes or no? Right? So, an e power x dx 0 to 1, if you integrate this, you get e. So, e power 1 minus e power 0 is what you get. So, e minus 1 is what you get, right? This is e minus 1. That means one thing for sure. Integral e power x squared dx 0 to 1, which is this area A, I can say for sure this area A, I can say for sure is less than e minus 1. But e power x squared is greater than 1 in the interval 0 to 1. Right? Is greater than 1 in the interval 0 to 1. This is 0, 1. And therefore, I can say integral 1 dx 0 to 1 is less than integral e power x squared dx 0 to 1. That means this A is greater than 1. So, integral e power x squared dx will be greater than 1 but less than e minus 1. So, that's like estimating integrals. I can't integrate this, but one thing that I can say is that this area will be less than e minus 1 but greater than 1. See, this was a crude estimation, right? As you grow, you'll learn many more techniques that will give you more sophisticated ways to estimate. They could be closer functions. You know, this was, I've compared e power x squared and e power x. I could have compared e power x squared with some other function and could have got a smaller interval than this. That would be a superior estimation. Superior approximation is what I would have got. You know what I'm saying? See now, can I wipe this off? See, this estimation we carry out in the event. See, it's not that nature will give me all functions that are integrable, right? Very often, in fact, most often I'll have functions that are non-integrable, but I want to find their definite integral, right? Therefore, I must be able to estimate, if not exactly evaluate, I must be able to estimate the range in which it lies, right? And with greater finesse, I can refine that estimation, make it better and better. Okay. Now, say I have integral 0 to 1 square root of 4 minus x squared minus x cubed. Don't even try to integrate this function. You'll spend a lifetime doing this and regret that you did this. You can't integrate this. Doesn't mean that nature will not throw up such a function. You might still be involved in estimating this function, right? So what you will have to do is you will have to compare it with closed functions which are integrable in turn, right? Now, in the interval 0 to 1, do you realize that x cubed will be less than x squared? When x lies in the interval 0 to 1, x cubed will be less than x square, right? Now, 4 minus x squared minus x cubed. Do you realize for sure it's less than 4 minus x squared? It's less than 4 minus x squared because it's 4 minus x squared minus a positive number. So it's less than 4 minus x squared. But can I say that it's greater than 4 minus x squared minus x squared? Because if I compare these two expressions, subtracting x cubed is like subtracting a smaller number. Subtracting x cubed here is like subtracting x square is like subtracting a bigger number. So if I subtract a bigger number, I'll get a smaller number, isn't it? So this must be smaller than this. How about it? Take their reciprocals. The direction of the inequalities change. So then 1 by, this is 4 minus 2x squared then, which is a function very dear to our heart because it would be readily integrable. This or its square root would be readily integrable. So we like this. 4 minus 2x squared greater than 1 by 4 minus x squared minus x cubed must be greater than 1 by 4 minus x squared. Yes or no? Take their square roots. So 1 by root 4 minus 2x squared will be greater than 1 by root 4 minus x squared minus x cubed will be greater than 1 by root 4 minus x squared. Isn't it? Now in the interval 0 to 1 then, this greater than 0 to 1, this 0 to 1, this. We've been able to estimate this because this, you know, is sine inverse x by 2. This also is readily integrable. You can take 2 common, so root 2 minus x squared. Again integrable, right? So then, this integral is less than this number that I obtained and is greater than this number. So that's a certain level of approximation. Depending on the situation, we can approximate further, we can refine our approximations, we can reduce the error in this range. But then this was just to give you a feel that this is what the common practice is. At this level, at your level, maybe this. Say I have, again, can I wipe this off? One plus x power 6. You can't integrate this. Try hard. You can't integrate this. Just trust me on this. Okay. But then we can estimate this. We can certainly estimate this. Now 1 plus x power 6 in the interval 0 to 1, do you realize is less than 1 plus x squared? But of course is greater than 1 minus x squared. You know, take the reciprocal and square root 1 by root 1 minus x squared greater than 1 by root 1 plus x power 6 greater than 1 by root 1 plus x squared. Integrate both sides. Integrate throughout. There are no two sides here. This you know, sine inverse. This you know, logarithm. Right? So, right. So then you can estimate this. You can again refine it further if required. Clear? So estimation is an important aspect of definite integrals. Okay? The richer your knowledge of functions and the richer your understanding of functions, the better will be your refinement. There are numerical techniques also that do this. There are a large number of numerical techniques that help you refine in a systematic manner, right? Now, say a property like this. See, integration is a process of summation, really. You know, when I talk of, definite integrals is a process of summation. When I talk of integral fx dx, x equal to a to x equal to b, then what I'm actually talking of is like selecting an x here, a small strip of thickness dx. This is like fx, right? So this is one sample strip. I take this sample strip and the area of the sample strip is fx into dx. Fx into dx is the area of the sample strip. Now what I do is I break it up in the entire interval from x equal to a to x equal to b. I break it up into infinite number of such sample strips of dx, 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 fx into dx, fx into dx, fx into dx. And I sum up all the fx's, fx into dx's. When I do that, I get the area under the curve. And that area is actually given by integral fx dx a to b. So when I talk of this is actually a summation of this kind. Sum of all the fx into dx, fx into dx, fx into dx for all x's from a to b, infinite such strips are summed up. Right? Now, if it's summation, realize that the properties of summation that we have learned could be applied to this. One of the properties that we've learned for summation is x1 mod of x1 plus x2 plus xn. Modulus of the sum will be less than or equal to sum of the moduli. Sum of the modulus of the sum will be less than or equal to sum of the moduli, right? An extension of triangle inequality, Therefore, if this is a summation of all the fx into dx's, then all properties of summation will apply to this. So this is like modulus of the summation, which will be less than or equal to, this integration is like the summation, this integral sign is like the summation sign, right? Is like the summation sign. It directs you towards a summation. That's what this integral does. So this would be less than or equal to sum of the modulus, sum of the moduli. This would be sum of the moduli, mod fx1, and then next mod fx, and then next mod fx into dx, and then next mod fx into dx, and so on and so forth. Modulus of the sum is less than or equal to sum of the moduli. So this is another property that you want to take stock of. Clear? Right? Now, suppose we have f and g as two functions. Fx and gx are two functions, right? Then can I say this? Fx minus lambda gx whole squared is always greater than or equal to 0? Real valued functions, this will always be greater than or equal to 0. Yes or no? So can I say f squared x, which is like fx whole square, minus 2 lambda fx into gx plus g squared x is greater than or equal to 0? Can I say this? Lambda squared, lambda squared g squared x greater than or equal to 0. Now let me take the integral from a to b of the entire thing. So integral of this from a to b minus integral of this from a to b plus integral of this from a to b will be greater than or equal to 0, because if this function is greater than or equal to 0, its integral from a to b will be greater than or equal to 0, right? Or taking the last term first, integral g squared x dx from a to b minus 2 lambda integral a to b fx gx dx plus integral f squared x dx a to b will be greater than or equal to 0, yes or no? Right? Do you realize that this is a quadratic in lambda? See, you will have like something, this is a number into lambda squared minus 2 lambda into something, this is also a number, plus a constant, this is again a number when you take the limits, is greater than or equal to 0. Yes or no? Which means a quadratic in lambda greater than or equal to 0. That means its discriminant will be less than or equal to 0. If a quadratic is greater than or equal to 0 always, then its discriminant will always be less than or equal to 0, right? So the discriminant of this quadratic will always be less than or equal to 0. Discriminant of this quadratic less than or equal to 0 would mean a to b fx gx whole squared will be less than or equal to integral g squared x dx a to b into integral f squared x dx a to b. Can this be said? What is this equivalent to? Cauchy-Schwarz inequality. Summation ai bi whole squared less than or equal to summation ai squared into summation bi squared. That was Cauchy-Schwarz inequality, right? That was Cauchy-Schwarz inequality. Summation ai bi whole squared less than or equal to summation ai squared into summation bi squared. That's the equivalent of Cauchy-Schwarz, but this is not called Cauchy-Schwarz. Some Russian joker said, okay, let Cauchy be there. This joker was called Bunyavosky. Tongue twister. So he said, since it looks like Cauchy, I'll have Cauchy there, but let me also be there. Bunyavosky. Cauchy-Bunyavosky inequality. This is called Cauchy-Bunyavosky inequality. We'll only call it the Cauchy inequality, right? It's comfortable doing that. Clear? Does it make sense? So this is yet another important property of definite integrals. Now, can I wipe this off? If I have a function fx and in an interval a to b, say the maximum value of fx was capital M. If M was the maximum value of the function in the interval a to b, capital M, and small m was the minimum value of the function in the interval a to b, right? Then I can say integral fx dx a to b, integral fx dx a to b will be less than or equal to integral m dx a to b will be greater than or equal to integral small m dx a to b, right? Which means integral fx dx a to b will always be less than or equal to capital M will come out into b minus a, will be greater than or equal to small m into b minus a. Right? Which means I can say integral fx dx a to b will be some number L into b minus a, where L would be less some number lying between capital M and small m. Can this be said? Think about it. This is then L, where L is smaller than capital M and is larger than small m, right? Now if fx is continuous in the interval a to b, right, then say if small m was the minimum value of the function and capital M was the maximum value of the function, and if the function is continuous in the interval a to b, then it will assume all possible values between small m and capital M, and therefore will it also assume a value L? It will also assume a value L, because L lies between small m and capital M. If it's a continuous function, it will assume all values between its smallest and greatest values. L is a number between its smallest and greatest values. Therefore, the function fx, if continuous, will assume a value L for some x equal to c, right? Therefore, there would be at least one c in the interval a to b for which the function assumes a value equal to L. Yes or no? That means I could have said that this will be some fc into b minus a, where c is some number between a and b, where c is some number between a and b. This is the mean value theorem in integral calculus. This is the mean value theorem for integral calculus. Good. Can I wipe this off? Right. Now, see, some of the very commonly used properties in definite integrals. Very commonly used properties. Integral 0 to a fx dx is integral 0 to a f of a minus x dx. This, in my opinion, is the most commonly used property in definite integrals. Now, the way to establish this property, start from the right hand side, take a minus x as some z, for example, right? Then dx will become minus dz, dx will become minus dz. Then this integral a minus x is z and dx is minus dz. I'm going from the x domain to the z domain. So then the limits will also be in terms of z. Okay. So when x is 0, z will be a. When x is a, z will be 0. Now, I can use this minus sign to interchange these limits, right? So we are all talking of the right hand side. So I interchange these limits and absorb the minus sign. 0 to a f z dz. Now, whether this is z, or this is x, or this is y, or this is p, or this is London, or this is Patna, does not matter, right? So might as well call it x. 0 to a fx dx, right? So integral 0 to a f of a minus x dx will be 0 to a f of x dx, right? Now, just to give you a couple of examples, can I wipe this off? Say, I have a function like this, 0 to pi by 2 sin x by sin x plus cos x dx. Something like this, okay? This will be, now 0 to a f of x dx will be 0 to a f of a minus x. That means sin 90 minus x, right? Sin 90 minus x. Replacing x by 90 minus x, a minus x. Sin 90 minus x plus cos 90 minus x. Yes or no? 0 to pi by 2. That's this integral I, which you realize is integral 0 to pi by 2 cos x dx divided by sin x plus cos x. Now, if a equals b, then each will be half their sum. That means if this is equal to this, then each will be half their sum, right? Half their sum means half of 0 to pi by 2 sin x plus cos x divided by sin x plus cos x, which would be pi by 4. Yes or no? Right? Say I have integral sum fx by fx plus f of a minus x dx 0 to a. Suppose this integral sum fx by fx plus f of a minus x 0 to a. Then I can replace x by a minus x from the property. So this is like integral f of a minus x dx divided by, if I replace this x by a minus x, this will become fx and this will become f of a minus x. So fx plus f of a minus x 0 to a. Now if a equals b, then each will be half their sum. So each will be half of 0 to a fx plus f of a minus x divided by fx plus f of a minus x dx. This will be a, so a by 2. This will be a by 2. Got it? Say if I have, in a very general sense, some function g tan x, a function of tan x divided by g tan x, a function of tan x plus g cot x dx 0 to pi by 2. 0 to a fx dx, I can replace x by 90 minus x here, right? So this integral I, replacing x by 90 minus x, this is g of cot x. Replacing x by 90 minus x, this will be g tan x plus g cot x. If a equals b, then each will be half their sum. Do you realize that their sum is 1? This plus this is 1. Do you see that? So each is half their sum. Half of their sum, which is 1 dx 0 to pi by 2. So that makes it pi by 4. Got me? Suppose we had integral x by 1 plus sin x dx 0 to pi, right? Call it I. I can replace x by pi minus x, right? One plus sin pi minus x will be sin x. 1 plus sin pi minus x, which is the same as sin x, 0 to pi. Then each will be half their sum. Each will be half their sum. So this is half of 0 to pi. This plus this. But this plus this would cause x to get cancelled. You are left with then pi divided by 1 plus sin x dx. right? How do you integrate this? Huh? Please tell me. Yes, yes, some of you. Right, multiply numerator denominator with 1 minus sine x. That's the best thing to do here. So this will be like 1 minus sine x divided by 1 minus sine squared x. Multiplying by 1 minus sine x, this will become 1 minus sine squared x, which is cos squared x dx, 0 to pi. And 1 by cos squared x is sec squared x tan x, and this is sec x tan x. Sec x tan x will be sec x. Yes or no? Got me? Now, let me look at the next property. The brother of this property, integral fx dx a to b, would be integral fx dx, I'm sorry, f of a plus b minus x dx a to b. In ranking, this is almost as good as the previous property in terms of the application that it provides. What we do is we start from the right hand side because there is more activity to be done on the right hand side. So might as well call this odd looking entity as some z. I then migrate from the x domain to the z domain. And then easy to see that dx is minus dz. Easy to see that dx will be minus dz, right? And the right hand side is then deemed as f of z. I chose this as z. And then dx in terms of dz will be minus dz. All right, now the limits also in terms of z, right? When x is a, z will be b. When x is a, lower limit, then z will be b. So z becomes b when x is a. When x is b, z will be rendered a. Yes or no? I use this minus sign to swap the limits. So deploy the minus sign for very noble cause a to b, right? Why z? Why not t? Why t? Why not x? Right? It does not matter whether I have z here or I have x. So might as well have x so as to have uniform looks, right? So this then is a to b fx dx. What do you say? So integral a to b f of a plus b minus x will be a to b fx dx. Very potent property, simple but potent, right? Now let me look at an application of this property, right? Integral pi by 6 to pi by 3 dx by 1 plus root tan x. Let me do this. Right? Integral fx dx a to b will be integral fx dx would be integral fx dx a to b would be integral f of a plus b minus x. That means this x could be replaced by this plus this minus x. And do you realize that a plus b minus x is like pi by 6 plus pi by 3 minus x? That's a plus b minus x. This is pi by 2 minus x. So it's as if I'm replacing x by 90 minus x, right? So then a plus b minus x, pi by 6 to pi by 3 dx by 1 plus square root of tan a plus b, which is 90 minus x, right? Sounds good? Let me call this I. Pi by 6 to pi by 3. This is 1 plus root cot x. 1 plus root cot x. Root cot x is like 1 by root tan x. So 1 by root tan x. Root cot x is like 1 by root tan x. That's what I did here. This will then be like root tan x dx by 1 plus root tan x pi by 6 to pi by 3, right? Now if this is equal to this, then each will be half their sum, right? So each will be half their sum, pi by 6 to pi by 3, and their sum, this plus this is 1, their sum is 1. Do you realize that? It will become 1 plus root tan x divided by 1 plus root tan x, that makes it 1 dx. So that's like half of pi by 6 minus pi by 3. That's the integral. Pi by 3 minus pi by 6. Pi by 3 minus pi by 6. This is pi by 12. This makes it pi by 12. Right? Not me, no? No confusion? Shall we proceed? Good. In a more general sense, if I had, say, integral fx by fx plus f of a plus b minus x dx, a to b, then I can replace all the x's here by a plus b minus x. I can replace all the x's by a plus b minus x. So f of a plus b minus x divided by f of a plus b minus x. Then replacing this x by a plus b minus x will give me f of x. If you replace this x by a plus b minus x, it will give me f of x. So if this is equal to this, then each is half their sum. So each will be half their sum, and their sum, as you can see, is 1. X runs from a to b, which is simply b minus a by 2. Right? Let me look at another property. I do not know if it's the third property. Don't bother about that. Integral minus a to plus a fx dx is 0 to a f of x plus f of minus x dx. Integral minus a to a fx dx is going to be 0 to a f of x plus f of minus x. Right? Now what we do is we start from the left hand side, minus a to a fx dx. Right? I'll take from minus a to a, what I'll do is I'll take it from minus a to 0 and then 0 to a. I'll take it from minus a to 0 and then I'll take it from 0 to a. Right? Right? Now, I don't tinker with this 0 to a fx dx, it's already there. Let me just plan out this one. Minus a to 0 fx dx. Let me deal with this. Right? So, just this part. Minus a to 0 fx dx. Wish it was a here. Wish it was a here. So what? Take z equal to minus x. So when I go to the z domain, this will become plus a. Taking z equal to minus x will do the trick for us, because then this will translate into plus a in the z domain. When x is minus a, z will become plus a. So this is a suitable transformation from what we need out of the situation. Clear? So then dz will be minus dx, and then going into the z domain, this will become f of minus z, and then dx will be minus dz. Now when x is minus a, z is plus a, because that was the whole objective. When x is 0, z is 0. Yes or no? Now how do I use this minus sign? Interchange the limits, right? 0 to a f minus z dz. Aha, I don't want z here. Replace z by x, who cares, right? So this is 0 to a f of x dx. So this part becomes 0 to a f of x dx. And if this part becomes this, then this sum of these integrals will be integral of the sum 0 to a f of x plus f of minus x dx. Again, I rate this property very high, very high. Maybe the first one, the best, the second one, the second best, and this one almost as good as the second best. Alright, so very highly rated property in terms of application. Integral minus a to a is 0 to a f of x plus f of minus x. If f is an odd function of x, then f minus x plus fx will be 0, and this integral will be 0. If f is an even function of x, then this will become twice 0 to a fx dx. Yes or no? Right? So this will be 0 when f is odd, and this will be twice 0 to a fx dx when f is even. Right? Say I have integral cos x by 1 plus e power x minus a to plus a. Right? I could write this as integral 0 to a f of x plus f of minus x. F of x is this. F of minus x. Cos minus x will be cos x. 1 plus e power minus x dx. And do you realize that this is like 0 to pi by 2? Writing this as 1 by e power x, so it will be simply cos x dx. Simply be cos x dx. Is it not? Write this as 1 by e power x. So e power x by 1 plus e power x plus 1 by 1 plus e power x into cos x. That's cos x. Right? So that makes it as simple as this. 1. The answer is 1 there. Clear? Proceed. I was just wondering how so many of you became such good fellows coming for the test. I'm still thinking about it. Okay. Next property. I might lose track of these numbers. You fix it if I do that. Integral 0 to 2a fx dx is 0 to a f of x plus f of 2a minus x. F of x plus f of 2a minus x. Good property, but not as widely prevalent as the previous properties. Let's go ahead and prove this property, right? So what I do is this 0 to 2a, I break it into 0 to a and then a to 2a. That's what I do, right? So this left hand side I deal with as follows: 0 to 2a f of x dx is 0 to a f of x dx plus u plus a to 2a f of x dx. Right? Now this is all right. I needed this. I'll not tamper with this. 0 to a f of x dx has already appeared. Part of it is okay. Now I just need to deal with this. I need to show that a to 2a fx dx is 0 to a f of 2a minus x. Isn't it? So I just deal with this and establish that this is equal to 0 to a f of 2a minus x. So 0 to, I'm sorry, a to 2a f of x dx. What I do is I write 2a minus x as some t, because when x becomes 2a, this t will become 0. When x is a, t will be a. So I'll have like a to 0 kind of a thing. The limits would be intact and then I just need to deal with the rest. So this is my rationale for choosing this transformation from the x domain to the t domain. Clear? Now when I do this, obviously you can see that dx will be minus dt and this will be f of x. X is 2a minus t, f of 2a minus t, and dx is minus dt, minus dt minus I have already plunged. Now, the limits also would have to be in terms of the new emperor t. So when x is a, t is a. When x is a, t is a. When x is 2a, t will be 0. Why is this minus sitting there? What should it be doing? It should swap the limits. So 0 to a, f of 2a minus t dt. Why is this t there? Replace it by x right here. Let me not waste more energy. So this part, which was a third, a to 2a fx dx, turns out to be 0 to a f of 2a minus x. That means this part has come through. Clear? Now, let's apply all the properties that we have learned, at least most of them, in one single situation. Right? Including this. Can I wipe this off? I'll allow it to stay resident for a while so that you can visually connect. Again, the next integral that I'm going to obtain for you is not just with a view to illustrate, but also with a view to give you a standard result. The next integration would be a standard result also. For the sake of my class, use it readily without giving me evidence of how it came, right? But in the class, I'll establish that result, so it will become a standard template for you from now on. All right? The integral that I'm talking of, 0 to pi by 2 ln sin x. Zero to pi by 2 ln sin x. Trust me, if I don't give you these limits, there is no way on earth you can tell me what integral ln sin x is. That means you can't ever tell me the primitive of ln sin x. But that doesn't mean that the definite integral will not exist. I must tell you this. It's possible that the definite integral exists, but the primitive does not exist. This would be one instance where, if I just gave you integrate ln sin x, you will do that forever. You will never get to the point. All right? But if I give you 0 to pi by 2 ln sin x, which means, well, I'm talking of an area under the graph of y equal to ln sin x from 0 to pi by 2. It's possible to get an exact value of that area. Although I may not get the primitive of ln sin x, may not be able to find a function which will never be able to find a function which on differentiation gives me ln sin x, but this one is achievable, as you will witness in a while. Okay. Now 0 to a fx dx, you would be tempted to apply 0 to a f of a minus x. Sin 90 minus x will be cos x. What good is this? No good. Each will be half their sum at least. Let's go ahead and see if that makes sense. If a equals b, then each will be half their sum. Right? So each then is like 0 to pi by 2 ln sin x plus ln cos x. Half of their sum. Ln sin x plus ln cos x is ln sin x cos x. Sin x cos x is best when it's half sine 2x. Right? Right now we're just being frivolous with things. We do not know where we are heading, but down the line we are hoping that nature will start obliging. Right? So this is half 0 to pi by 2 ln. This is sine 2x by 2. So sine 2x minus ln 2. Sine 2x by 2 means sine 2x ln sine 2x minus ln 2. Ln a by b is ln a minus ln b. Ln. Yes or no? है ना? So far so good. Now just look at 0 to pi by 2. See, this is all right. This ln 2 is all right. I don't want to do further amends to this. I'll allow it to reside there as it is. Let me deal with 0 to pi by 2 ln sine 2x. Let me just deal with that independently for a while. Ln sine 2x dx. Right? Now, if I change the subject of integration to 2x, if I change the subject of integration to 2x, that means this becomes d of 2x, but I balance it this way. Yes or no? Now, if x runs from 0 to pi by 2, 2x will run from 0 to pi. Khatam, 0 to pi. So far, so no, abhi tak nothing good has come through. But so far, so good, right? So it's like ln sine t dt 0 to pi. Right? So this is like half of 0 to pi ln sine t dt. Where t is 2x. Where t is 2x. Now, we didn't need a 0 to pi here. We needed a 0 to pi by 2. Let me go back to 0 to pi by 2 where it all came from. That means I want to half the upper range. See, 0 to something is 0 to half that something with this. This is the result. 0 to something, if I want to convert to 0 to half something, then this is the result that comes in handy, isn't it? 0 to something to 0 to half that thing, right? So 0 to something to 0 to half that thing, that means 0 to pi by 2, right? 0 to half that thing, right? Now that's going to be 1, of course, this will come through identically. So ln sine 2 will stay back. Ln sine t will stay back, plus f of 2a minus, that means f of this minus this, right? That means ln sine t, this t would have to be replaced by pi minus t. This t would have to be replaced by pi minus t. See, this is 2a minus x. That means pi minus t, right? So ln sine pi minus t, but sine pi minus t is the same as sine t. Do you realize then that this is the same as 0 to pi by 2 ln sine t? Yes or no? Then why t? Why not x? Right? Which means integral 0 to pi by 2 ln sine 2x that we had is 0 to pi by 2 ln sine x dx. Yes or no? I could do this. See, we started with this 0 to pi by 2 ln sine 2x dx, which turned out to be the same as 0 to pi by 2 ln sine x dx. Isn't it? Can I just remove this and get back to the original form? Oh, so this then turns out to be half of 0 to pi by 2 ln sine x dx minus half ln 2, 0 to pi by 2, right? Half ln 2, 0 to pi by 2 dx. And this is I, that the original integral that we started with. And realize, what is this? I by 2. This is I by 2. So I minus I by 2. That makes it I by 2. This is I by 2, isn't it? This whole thing is I by 2. So I minus I by 2, that makes it I by 2 is, this will be pi by 4 ln 2 minus pi by 4 ln 2, right? Is minus pi by 4 ln 2. So I then becomes minus pi by 2 ln 2. So integral ln sin x 0 to pi by 2 and integral ln cos x 0 to pi by 2 both will be minus pi by 2 ln 2. Right? And why negative? Dekho, simple. In the interval 0 to pi by 2 or any other interval, sin x is less than 1. So ln sin x will be negative. So the graph of this in the interval 0 to pi by 2 will be below the x-axis. Therefore, this integral should have been negative. You expected this to happen. Yes or no? Can I wipe this off? Now, let me look at some properties of definite integrals that are related to periodic functions. All right. So properties related to periodic functions. Let's look at some properties related to periodic functions. All right. That means I have a function f of x, which is f of x plus t. T is the fundamental period of the function. And in my discussions, I will use m and n as integers. So I'm not going to state that, but m and n would be treated as integers in this discussion, right? Now, the first property is integral f of, if f is periodic, so I'm talking in all these cases a periodic function f, right? fx dx a to a plus t. A can be any number, any real number, a to a plus t. I claim will not depend on a. I claim that this will be independent of a. I claim that this will be independent of a. That means whether you plug in a equal to 1 or a equal to 2 or a equal to root 2 or a equal to minus root 3 plus root 7, this will bear the same value if t is the periodicity of the function fx. Right? Now see how it goes. Let's say the primitive of fx, let's say the primitive of fx is some phi x. That means phi x when differentiated gives me fx, right? That means phi dashed x is fx. Phi when differentiated gives me f. Phi dashed x is fx. Good. So then, if that be the case, if phi is the primitive of f, then this integral, do you realize, would be phi of a plus t minus phi of a? Yes or no? Right? Right? This is some function of a. This turns out to be some function of a, IA. I want to show that I is independent of a. If I is independent of a, then should I not have di dA 0 always? If in the expression for I, a never appears, then on differentiating I with respect to a, it should always be 0. Right? di dA must always be 0. So, I dashed a is phi dashed a plus t minus phi dashed a. How about this? Hey, do you realize phi dashed a plus t is actually f of a plus t? Phi dashed a plus t will be f of a plus t. Phi dashed a will be f of a. Right? So phi dashed a plus t is f of a plus t. This is f of a. But t is the periodicity of f, so f of a and f of a plus t will have the same value. This difference therefore will be 0. That means if I dashed a is 0 for all a, if I dashed a is 0 for all a, not for some a. See, if it's 0 for a certain a, then that a will be a local maxima, local minima and other things. Will be a critical point, but this is 0 for all a. That means there is no prevalence of a in the expression for I. I therefore must have been independent of a. This must, a must be independent of a. Independent of a means having the same value for all a. This expression IA therefore is independent of a, has the same value for all a's. Right? This was now taught to you like a property, but the first time, let me tell you, I came across this was in my IIT JEE exam. This was never there in the books that we had, was never learned by us as a property. This, the first time got connected with this was in the exam hall while we were taking the IIT JEE exam. This is where we saw this problem. Okay. Now, of course, it's served to you on a platter with love and affection. Can I wipe this off? Again, the next property, 0 to n times t, n is an integer, is n times 0 to d fx dx. Now that's not difficult to see geometrically, because you realize that the function, say 0 to t, it's like this, 0 to 2t, it's like this, right? Because it's periodic, it will replicate its character every t units, t to 2t to 3t, and so on and so forth. Yes or no? So if I have to say 0 to n times t, that means I'm talking of n such units, 1, 2, 3, 4, n such units, area under n such units would be n times the area of this unit, would be n times the area of this unit. That's a geometrical way of looking at it, right? So it just validates the result, but let me also give you an algebraic proof for the same, right? Shall we proceed? Now 0 to nt fx dx, I could write as 0 to t, t to 2t, 2t to 3t, 3t to 4t, 4t to 5t, r minus 1t to rt, n minus 1t to nt. I could do that, right? Isn't it? Right? 0 to nt, I break it up as 0 to t, t to 2t, 2t to 3t, 3t to 4t, then some element r minus 1 t to rt, and then eventually last would be n minus 1 of t to n times t. N such integrals, n such integrals. So the n such integrals compacted as summation integral fx dx r minus 1 t to rt, where r runs from 1 to n. Yes or no? Bolo. When r is 1, it will be 0 to t. When r is 2, it will be t to 2t. When r is 3, it will be 2t to 3t. When r is n, it will be n minus 1t to nt. Yes or no? Right? I want this 0 here. And I want a t here for all r's, for any r. I want a 0 here and I want a t there. I want a transformation. I need a transformation that will do that. I want to go from, let's say, some x domain to z domain, where in the z domain, I'll have the heavens available, 0 and t there, right? Then the conjecture is, I do like a x minus r minus 1 times t for any r as some z. I go from the x domain to the z domain with this transformation, because then when x is r minus 1t, shunya, and when x is rt, it will become t. So z runs from 0 to capital T, the limits that we were looking for. How's that? Right? So then, this is like summation r equal to 1 to n integral. In the z domain, I am going to the z domain, where dx is the same as dz. Right? And the limits, when x is this, z is 0. When x is rt, z will be t. And f of x becomes z plus r minus 1t. And dx is the same as dz. Tell me if you doubt this. No? So fz plus f of z plus r minus 1 t, is what I get out of this. Hey, f of z plus an integer, r minus 1 is an integer, times t, that's going to be f of z. F of z plus an integer times t will always be fz, because t is the periodicity of the function, right? So this is going to be fz for sure. So this is summation r equal to 1 to n integral 0 to t fz dz yz. Yes. And how many such integrals? For r equal to 1, one such integral. For r equal to 2, the same thing. For r equal to 3, the same thing. For r equal to n, the same thing. So we have n such identical integrals. So then each will be n times 0 to t, this summation removed, fx dx. Geometrically, we could see that this ought to have been the case, right? Can I wipe this off? Proceed. Some more properties. Although I can tell you that by and large, we don't go past these properties in periodic functions, but a formality to communicate some more properties. Just to give you, how the previous property could be used. Say, for example, e power fractional part of x dx, x runs from 0 to 100. See, the property that we learnt is integral for a periodic function with periodicity t, 0 to n times t is n times 0 to t fx dx. That's the property that we just learned, right? Now, is fractional part periodic? What is its periodicity? 1. 1 is its periodicity. So this is 100 into 1. So it's like 0 to n times t. This n can come here. So this n is 100 here. 0 to 1 e power fractional part of x dx. Hey, but in the interval 0 to 1, fractional part of x is the same as x, na? When x lies in the interval 0 to 1, fractional part of x is the same as x. So this is 100, 0 to 1 e power x dx. So which is 100 into e minus 1. Clear now? Can I wipe this off? As a student like you, I knew only two properties. 0 to a fx dx and a to b fx dx is like a to b f of a plus b minus x. This is it. No, we also knew minus a to a fx dx as 0 to a fx plus f of minus x. This was it. We didn't know more than this. The rest was simply out of deriving it from first principles in the exam. Everything was derived from first principles. So many properties were never known to us. Let's learn some more then. See, when you start relying on your fundamental instincts on the subject, you are a better problem solver. When you are dependent on a large number of results, then half your processor is occupied with, juggling with that many results. you know, this, that. But times have changed, People don't want to count on first principles, don't want to count on fundamental instincts. They want to believe in a large number of ready-made results. Very handy. So that's the only reason I teach so many properties. Not that I believe in all of this. I believe in just knowing the basics right and entering the exam with the confidence of doing it from scratch. Okay. Let me teach you another property. A plus nt to b plus nt fx dx is a to b fx dx. Is a to b fx dx. Hey, I want this a, I want this b. Right? This is what I want. I use this transformation. X minus nt is z. Yeah? So then, when x is a plus nt, this will become a. When x is b plus nt, this will become b. Good enough for us, right? So then the left hand side is integral. And see that dx is the same as dz. We'll go from the x domain to the z domain. Dx is dz. X becomes z plus nt. And when x is this, z will be a. When x is this, z will be b. Isn't it? But f of z plus nt is the same as f of z. Perfect. A to b f of z dz. Yz x. A to b fx dx. Right? Can I wipe this off? I don't think I ever used this property. Now, if you think about it, it's the graph, it's the area under the graph of fx from x equal to nt to x equal to mt. है ना? सोचो, think of it like this: from x equal to nt to x equal to mt. Now, how many t's are here? M minus n t's are here in this, right? Each of length t, right? M minus n units, there are m minus n units, each of length t, right? So, 1 unit of length t, another unit of length t, and how many such units? M minus n such units. M minus n such identical units of length t, right? So, you should expect this to be m minus n 0 to t fx dx is what you should expect. M minus n 0 to t, because each of these is t units, which will be the same as the graph between 0 to t, isn't it? So you would expect this to be m minus n 0 to t fx dx. But let's also get past this algebraically, purely algebraically. This is m minus n 0 to t fx dx. Right? Let's see how this comes through algebraically. Hey, what's a big I want to make this 0. So, right, very good. X minus nt as z, because this will turn 0 then, right? So, if that happens, dx of course would be rendered same as dz, going from the x domain to the z domain, right? And this becomes, x becomes z plus nt, dx is the same as dz, and when x is nt, z is 0. When x is empty, z will be m minus n into t. But f of z plus nt is the same as f of z. M minus n is an integer, f of z dz. Hey, I told you, if t is the periodicity, this m minus n can come here. That was an earlier property. So this is like m minus n 0 to t fz dz, right? This one maybe I might have used somewhere, but I don't recall. Huh? Yes, yes, yes. Absolutely, you could do that. Absolutely. That means area from 0 to empty minus area from 0 to empty. Perfect. So what he's saying is, absolutely, he's saying we could have done this. This is like area from empty to empty. What we could do is, that's like area from 0 to empty minus area from 0 to empty. Area from empty to empty is like same as area from 0 to empty minus area from 0 to empty. Perfect. So, well said. 0 to empty fx dx minus 0 to empty fx dx. This m can come here, this n can come here from the previous property, which is like m minus n 0 to t fx dx. Good. Right? Okay. Now, what I'm going to teach you, way back in class 11, you know, when you asked me a problem, I said, you got some book and said, when you just started to, you know, rise above the ground, you gave me a problem and I said, no, this is not the time I'll solve this problem for you. But now that problem can be solved, because I'm going to teach you what's called Newton-Leibniz. Newton-Leibniz, that's the idea. Way back, remember? So, Newton-Leibniz the fellow must have been God, Newton. He is there everywhere, just about everywhere. Think of it, and he's there. The only place, only sphere where I don't find Newton available is number theory. See, he's not there in number theory, where, you know, number theory is predominantly Euler and Gauss. And after that, Erdos came in, who gave a lot of primality issues related to number theory. But number theory perhaps is the only area Newton didn't touch. But then he didn't have to, because, you know, he was the god of continuum, so he didn't bother about discrete mathematics. Number theory is like discrete mathematics, but he gave the idea of continuum, calculus, everything is, you know, courtesy Newton. And of course they say even Leibniz, because Newton eventually offended Leibniz offended Newton, saying that he plagiarized, but they were not that low to plagiarize. They were gods. Each came up with the idea of calculus independently. But then they got into a tussle about who came up with this idea first. Both must have come up independently actually. But then let me tell you, Newton Leibniz as is applied in definite integrals, which is differentiation under the integral sign. Okay, that is to say that if I have an integral where the lower limit is a function of alpha, some parameter alpha, the upper limit is also some function of alpha, a parameter alpha, and I have a function f x and includes a parameter alpha, a function of x and alpha, where I am going to integrate with respect to x. Alpha is a parameter prevalent in this, and I would have dx. Now, obviously, when I integrate it with respect to x, this will be a function of alpha. This will be a function of x and alpha. When I integrate it, forget the upper and lower limits. It will be a function of x and alpha when I integrate with respect to x. But then when I supply the limits, the x's that will come will be replaced by the upper limit, b alpha, and then minus the lower limit, a alpha. So then eventually x will vanish. This whole thing will be a function of alpha. This entire thing, eventually when I supply the limits in terms of alpha, will be a function of alpha. X will dissolve. Right? This x is only temporary. In a definite integral, this x is only temporary. It will go into oblivion the moment I supply the limits. Right? So this, to say the least, is a function of alpha, the parameter alpha. Now Newton Leibniz gave us this result, which is called differentiation under the integral sign. That means I want to find dI alpha, that is I dashed alpha. I will not offer a proof for this result, but must tell you that of all the definite integrals that I am going to teach you, or I have taught, this would be the favorite, both from the point of view of number of problems that you solve and also its importance in an exam. Right? I mean, they set problems based on this result upfront. Okay. So, without proof though, I dashed alpha, that means dI alpha, differentiating I with respect to alpha, gives me three terms. Get handle over the three terms. In the first term, there is this integral a alpha b alpha, where f is differentiated with respect to alpha, keeping x constant. Is differentiated with respect to alpha, keeping x constant. That means it's like dou f dou alpha dx. That's the first term. Differentiating f with respect to alpha, keeping x constant. That's the first term. Right? In the second term, the integral is not there. In the second term, in this function, wherever x appears, it's replaced by the upper limit b alpha. That means f, the x is replaced wherever it appears by b alpha, and the alpha that was already there stays put in this function. And then b is differentiated with respect to alpha, db d alpha. That's the second term. Right? There is a third term in this. The third term comes with a minus sign. In the third term, again the integral is not there. This x is replaced by the lower limit a alpha. Is replaced by the lower limit A alpha. And the alpha maintains its position wherever it was in the function. It stays there, and then A is differentiated with respect to alpha into dA d alpha into dA d alpha. These are the three terms. So what is it? In the first term, when I differentiate I with respect to alpha, switch it off. When I differentiate I with respect to alpha, in the first term, the integral, where this is differentiated with respect to alpha, keeping x constant. So dou f dou alpha dx, and then integrated. In the second term, this x is replaced by the upper limit b alpha alpha and db d alpha. In the third term, this x, there is a minus sign that comes with it. This x is replaced by a alpha alpha, and then a is differentiated with respect to alpha. These are the three terms for differentiation under the integral sign in a very general sense, most general form, right? Let's understand this. Let's get handle over this. I mean, can I wipe this off? Look at this. Integral alpha x plus alpha squared dx this varies from, say, alpha squared to alpha cubed. This is I alpha. Right? So let me just say alpha squared x squared. The reason I did this was, sine alpha x plus alpha squared you could readily integrate. काय को ये सब उल्टा पुल्टा कर रहा है यार, इंटीग्रेट ही तो कर सकता है डायरेक्टली, फिर डिफरेंशिएट करेंगे. नाउ दिस यू कांट इंटीग्रेट, ट्राई हार्ड. I have added an x squared to add to your plight. Okay, so I dashed alpha then will have three terms in it, right? This is a alpha, a function of alpha, alpha squared. B alpha, a function of alpha, alpha cube, right? I dashed alpha. In the first term, we'll preserve the integral. We'll only internally alter it. Internally alter it means I'll differentiate this with respect to alpha, keeping x constant, which would give me, from chain rule, first differentiate this with respect to this, right? So if I differentiate this with respect to this, I get cos alpha x minus alpha squared x squared. Yes or no? And then differentiate this with respect to alpha, keeping x constant. So when I do that, I get alpha, I get x plus 2 alpha x squared, differentiating with respect to alpha, keeping x constant. Yes or no? Dx. That's the first term. Right? Oh, there is a plus, yes? There is a plus here. Alpha x plus alpha squared x squared. Clear? In the next term, replace this x. Wherever x comes, replace it by the upper limit, and then differentiate the upper limit with respect to alpha. Wherever x comes in this function, replace that by b alpha, and then differentiate b with respect to alpha. So then sine This x replaced by alpha cube, so alpha to power 4. This x replaced by alpha cube, so alpha to power 6 into alpha squared, alpha to power 8 into dB d alpha, that is 3 alpha squared. 3 alpha squared, that's the second term. Wherever x came, I replaced it by b alpha in this, and then differentiated alpha with respect to 3 alpha cube with respect to alpha. I got 3 alpha squared. Does it sound all right? Yes or no? In the third term, which will come with a minus sign, in the third term, wherever x came, I will replace it with the lower limit. That means this x and this x will be replaced by alpha squared. Yes or no? Minus sign. This will become alpha cubed plus x is alpha squared. So this will become alpha to power 4, alpha to power 6. And then differentiate this with respect to alpha. That gives me 2 alpha. That is I dashed alpha. That is I dashed alpha. Right? What you need to do is, at home, just rub against this expression, this a large number of times, so that your mind gets settled with this thought. Mind gets completely settled with this thought. Right? Now, in the event the lower limit is 0 or the lower limit is a constant, say it's independent of alpha, then this third term will be 0. In the event the upper one is independent of alpha, the second term will be 0. In the event this is independent of alpha, then the integral will be 0. You know what I'm saying? If this does not have any alpha in it, it has just x, when I differentiate it with respect to alpha, I'll get 0. Right? These are the 3 variations that could occur. Now, I want to integrate sine bx by x dx 0 to infinity. I want to integrate sine bx by x 0 to infinity. Right? Now, one thing let me tell you, if I have integral fx dx, just, but this is besides the point, this one just to add, because I missed out on this, and a is a constant 0 to a, or let me call it 0 to x, just to tell you the difference. If I have something like this, 0 to x fx dx, one thing that you must realize is that this x is not the same as this x. This x is not the same as this x, because if this I replaced by t, then it will have the same value, isn't it? That means the x that I showed here was not the same as this x. You know what I'm saying? Because if I replace this x by t, then 0 to x, this integral will remain the same. That means this x was obviously not the same as this x. Right? So, say if I had something like this, then this will be a function of x. But which x? It will be a function of this x, not this x. Right? The x that you see here is not the same as this x. It is independent of this x. Right? Now, therefore, just for convenience, for the first time I'll do this, but then later on I'll be direct in this. I write this as 0 to x ft dt. Right? Now, if I differentiate phi with respect to x, X is my parameter. I'll have 3 terms in it. I'll have 3 terms in it. In the first term, I'll have 0 to x, where I'll differentiate this with respect to x. Now this is independent of this x. Essentially differentiating this with respect to x, but which x? This x. So if I differentiate this with respect to x, what will I get? 0. Because this does not have this x in it. For this kind of a function, right? So this will be 0 dx. In the next, what would I do? I will replace this t with this x. So I'll get fx. And then I'll differentiate x with respect to x. Get 1. Right? In the third term, this is a constant independent of x. So if I differentiate this, I'll get 0. So anyway, 0. So then this turns out to be fx. So which means if I differentiate this with respect to x, I'll get fx. Right? That means d dx of 0 to x fx dx is fx. We'll use this often. Phi dashed x we got as fx. So that means d dx of this 0 to x is fx. Which x? Hey, this x, not this x. This is temporary. This is otherwise meaningless. Right? This x is fx. Clear? Right? Now let me come to this very beautiful integral. Can I wipe this off? When I entered the class today, my objective was to just give you a little bit of a scare, a half an hour crisp class, and then leave you at the mercy of the test. That's what I was intending doing. Unfortunately, plans don't work always. That's what Newton says is inertia. Okay. I want to integrate this 0 to infinity. Try integrating. Try finding a primitive and get bamboozled. You can't find a primitive because I couldn't. Now to deal with an integral of this kind, this is what they do. They start with e power minus ax sine bx by x dx, 0 to infinity. Now if I can find this, then the value of this at a equal to 0 will give me this integral. And we'll assume that a is greater than or equal to 0. Right? So the value of this at a equal to 0 will give me this integral. Now you will see why the choice of this integral, how it helped. Right? Now say if a is a certain fixed number only and b is a parameter, then this will be on integrating, it will be a function of b. A is a certain fixed number and b is allowed to be varied, then this will be a function of b on integrating and supplying the limits. Now I do a I dashed b, differentiate I with respect to b. That is di db is 0 to infinity. Nothing will change. These are, if I'm differentiating with respect to b, then these are like constants, x and this. So e power minus ax by x. This will give me x cos bx. On differentiating with respect to b, it will give me x cos bx, right? Yes or no? Right? So the x that was sitting in the denominator with acted like a thorn. We've been able to dump the x in the denominator by differentiating with respect to b. And we've got e power minus ax cos bx. This kind of a function you've integrated in the past. E power mx cos bx plus c integrated using parts and also using, this is real part of 0 to infinity e power minus ax e power ibx. Yes or no? Nahi kya? No? Huh? But do you understand this? Why this is the case? Hey, e power ibx is what? Cos bx plus I sin bx. What's the real part of that? Cos bx, which is this, isn't it? I haven't put you through a test on complex numbers yet, huh? Have I? Okay. So then, this is the real, you understand this, isn't it? The real part of this, which means this is like real part of 0 to infinity e power minus x a minus ib dx. Integral e power mx is e power mx by m, yaar. Yes or no? Minus I take out, this minus does not matter. X runs from 0 to infinity, right? Real part of this. Now, at x equal to infinity, this will become 0, e power minus infinity. So 0 minus, at x equal to 0, this will become 1 by a minus b. So 0 minus 1 by a minus b with a minus out, this will be real part of 1 by a minus b ib. No? That means real part of a plus ib by a minus ib, I'm sorry, by a square plus b squared. And the real part of this is a by a square plus b squared. Yes or no? Clear? Therefore, I dashed b, di db is a by a square plus b squared. So far so good? Can I just remove things and create some space? Di db turns out to be a by a square plus b squared. Right? Let me recover I. Di then is a by a square plus b squared db. Yes or no? Integrate both sides. Integral di will be I, the one that we are seeking. This was I that we were seeking, right? I, and this is tan inverse b by a. Yes or no? 1 by a. So that 1 by a will get cancelled with this tan inverse b by a, plus of course a constant of integration. Now, this is a fixed constant. This is not an arbitrary constant because I was a definite integral. So this c must have a fixed value. It's not an arbitrary constant. An arbitrary constant will appear in an indefinite integral. In a definite integral, this fellow need to be given a value. In a definite integral, this will have a specific value. If it was open-ended, indefinite, then the constant will be arbitrary, but in this case it will be a fixed known constant, right? How do I determine that? This is IB. Hey, what is I0? Put B equal to 0. I0 will be 0. So, putting B equal to 0, tan inverse 0, 0, plus C is IB, I0. I0 is 0 as you can see. Put B equal to 0, I will turn out to be 0, right? So, when B is 0, I is 0, leading to C equal to 0. Yes. Which means I, which we have recovered now, with C equal to 0 is tan inverse B by A. Is tan inverse B by A. Now. This integral is what? This one is limit IB as A tends to 0. As A tends to 0, you should get this? Yes or no? So the given integral, let me call it G. The given integral G is what? The given integral is G is limit IB as A tends to 0. As A tends to 0, this integral will tend to G. Right? Now, as A tends to 0 here, what will this be? Yes? As A tends to 0, tan inverse B by 0. I have a divided house here. Be unambiguous, come on. As A tends to 0, IB will tend to what? Sure? Not always. If B is positive, it will tend to pi by 2. If B is negative, it will tend to minus pi by 2. It will either have a value pi by 2 or will have a value minus pi by 2 depending on whether B is positive or negative. So for B positive, it will be plus pi by 2. For B negative, it will be minus pi by 2. That means G will be pi by 2 when B is positive and will be minus pi by 2 when B is negative. So this integral sin bx by x dx 0 to infinity is either plus pi by 2 if B is positive or will be minus pi by 2 if B is negative. And of course when B is 0, it's going to be 0. Yes or no? And you expected that because if you replace B by minus E, the sign of this integral will change. Isn't it? So if it had a value, then for plus B, positive B's, it will have one value, but for negative B's, it will have negative of that value if this was integrable. Right? So this is plus pi by 2 if B is positive, is minus pi by 2 if B is negative. Yes or no? What mod? Then pi by 2. If you took the mod of this, then it will always be pi by 2. Mod G will always be pi by 2. Right? So again, for the sake of my class, integral 0 to infinity sin bx by x dx, known as pi by 2 or minus pi by 2, to be looked upon as a standard result for my class. I will have to stop dumping more resource on you. I'll have to stop here, although I'm tempted to continue long. Two things prevent me from continuing further: the pain and of course your sad looks. But you know what? A lot more to be done. But with what we've done today in terms of the properties, spend this week solving problems from Cengage on definite integrals. You are equipped, more or less equipped, to solve problems from Cengage definite integrals. Do that.